Hello, everyone. I'm Yaniv from IBM Almaden Research Center in San Jose, California. I'll present our work on adaptive multimodal reinforcement learning for online database tuning. Modern database management systems may have hundreds of configuration parameters. The settings of many of these configuration parameters need to be tuned in order to optimize the database performance. In addition, the DBMS environment is dynamic, which means these configuration parameters need to be continuously monitored and tuned. The task of monitoring and tuning database configuration parameters is traditionally done by database administrators, but manually monitoring and tuning configuration parameters of a very large number of databases on the cloud is not scalable. For example, if we have 1 million database instances, we would need approximately 50 database administrators to take care of this administrative task. Several cloud providers have identified this challenge and developed solutions for automatic database administrative tasks at scale. One example is the Oracle Autonomous Database, which provides automatic provisioning, scaling, and tuning, as well as other capabilities. And Alibaba Self-Driving Database Platform that provides self-repair, self-optimization, and self-security. Automatic database tuning is a very active research area too. And here we follow previous works and use reinforcement learning to recommend knob settings to improve the database performance. And we propose an online tuning algorithm that can adapt to changing workloads. Our algorithm is based on multiple reinforcement learning models, which we're trained using the deep deterministic policy gradient algorithm, which is a reinforcement learning algorithm for continuous action space. In our case, the action is tuning database configuration parameters, which take continuous values, and therefore we use the DDPG algorithm. We also define a reward that measures the database performance improvement as a weighted sum of the database throughput and latency. The first step, we evaluate the reinforcement learning algorithm in an offline tuning setting, in which the workload is static, is not changing, and we use a benchmarking tool with the database, submit queries, and measure the database performance. In our case, we use Sysbench. It serves multiple purposes. We want to evaluate and fine-tune the algorithm. We want to obtain better knob settings for a given workload. And we want to generate preliminary pre-trained reinforcement learning models for online tuning. On the right side, in the plots, you can see the results of automatic tuning Postgres database for a Sysbench OLTP read-write workload, where we start with the database default configuration, then the reinforcement learning agent kicks in, explore different knob configurations, and eventually is able to significantly improve the database performance. We started with a throughput of 2000, and using the baseline, the default database configuration, and we ended up in around the throughput of around 10,000. In online tuning, the database and its environment are constantly changing. Workload can change in the course of the day. For example, during daytime, there can be a specific workload, and during nighttime, a different workload. The amount of available system resources can change too, and the database size can increase or decrease based on, depends on database updates. All of these factors affect the database performance. Out of these factors, in this work, we explore the problem of changing workloads scenario. And we are trying to answer the question whether a single pre-trained reinforcement learning model that was trained on a specific workload can adapt to new workloads. whether it can generalize to new workloads and how well it can generalize to new workloads. To answer this question, we developed a multi-model online tuning algorithm that detects workload changes, selects a set of reinforcement learning models as candidates for tuning from a pool of pre-trained models, where the models are selected based on constant similarity. Each model in the pool has an identifier, which is a workload representation vector, and compared using the cosine similarity to the current workload. The models which have the highest cosine similarity are being selected. In addition to the models that are selected from the pool of pre-trained models, we create a new model. And this is to make sure that always we get the best model to recommend the knob settings. In the case that we selected from the pool of models, a model which is suboptimal. All the models in the set of candidate models are being ranked using the beta distribution, and a model is selected to recommend knob settings based on its ranking, where the ranking is computed using the best beta distribution and the average model performance. The models are continuously being updated as workloads evolve. And each model, the best model for each workload, is persisted with its experience memory, workload representation vector, and the best knob configuration. Whenever we detect a workload change, we persist the best model from the previous workload with all of this information, with the experience memory, the workload representation vector, and the best knob configuration. To evaluate this algorithm, we compared it to the single model approach, in which one reinforcement learning model is used to recommend knob settings for different workloads. And we compare it also to the baseline database performance. We created an experimental setup in which every 50 time steps the workload is changing. And we selected 16 knobs for tuning and used 22 metrics to model the database state for the reinforcement learning agent. What we observed is that compared to the single model approach, the multi-model algorithm yielded better and more stable performance for evolving workloads. The multi-model approach improved the default database throughput by a factor 2 for an OLTP read-write workload and a factor of 5 for an OLTP write-only. To summarize, an online database tuning algorithm needs to adapt to changes in the database environment. We developed an online tuning algorithm for changing workloads. We observed that a single reinforcement learning model may not always generalize well to new workloads, and more than one reinforcement learning model need to be introduced. An experimental result showed that our multi-model approach improved the default database throughput by a factor of 2 for an OLTP read-write workload and a factor of 5 for an OLTP write-only, and had shown better stability than a single model approach.